So today we will deal with the first topic of EMF equation of DC machine. Let phi be the flux per pole in Webers. Okay, there may be two pole machine, four pole machine, but how much flux is under a particular pole? So this is the flux per pole, and Z is the number of armature conductors. And armature conductors is equal to number of slots and the number of conductors per slot. There are many slots in the armature conductor, and we have to, and few conductors are there in each slot. So calculate the total number of armature conductors. We have to multiply these two. Let P be the generator poles, number of generator poles, and A be the parallel paths. So what is this parallel path? Parallel path is the path through which the rectified current is taken out. N is the armature rotation. Eg is the EMF generated in any one of the parallel paths. Okay. And armature rotation is in RPM. This is to be taken into consideration. Okay. Because if we are taking the SI system, then SI system time, unit of time is seconds. So if we are required to change is into a RPS, then it will be N upon 60. Okay. And E is the EMF generated in any parallel paths of the armature. Now the formula of EMF is known to us. It is d phi by dt. Here we are assuming that number of turns is 1. Okay. So this is taken as n by, so it is taken as d phi by dt. Okay. Now, since EMF is the cutting of flux per unit time, okay, so let the flux which is cut per conductor, okay, in one revolution be d phi. Okay. So this is the small. So this will be equal to phi p, because phi is the flux per pole and p is the total number of poles. So since we are talking about the one revolution, the whole, all the poles will be considered in this case. Okay. Now the number of revolutions per second is n by 60. This is per time for one revolution will be dt, that will be 60 upon n. Okay. Flux cutting is also taken for one revolution. Time taken is also for one revolution. Now we can substitute these values in the d phi by dt. So substituting these values, we get the EMF generated per conductor in one revolution. Okay. So it is 5pn upon 60. Now if we are required to calculate the EMF generated for all the conductors, then we know that the total number of conductors are Z, so it becomes 5ZNP upon 60. Okay. So there are two types of windings. It is based on the we are having the windings, so how they are wound in the armature. Okay. So it can be of two types. One is the wave wound generator. So here the movement of the winding is in the shape of waves, and it moves forward every time. Okay. Although after one revolution it comes back. Okay. But it moves forward in a wave manner. And in the lap winding, we know what do you mean by lap? So in the lap winding, we start from the winding at a particular point and we go step by step further in a gradual manner. Okay. So the number of parallel paths in wave wound generators is 2. Okay. And in the lap wound generator, it is A. So this A is equal to Z. Okay. So when we substitute these parallel paths, so EMF generated per path becomes 5Z NP upon 120 for wave wound generator and 5Z NP upon 60A. You can say it is in general for lap wound also. Okay. So we are dealing with the generator, and from the principle of generator, I have told you that in generator electricity is generated and it is given to the load. Okay, but there are brushes in the DC machines. The role of the brush is to carry the rectified load and give it to the external circuit or load. Okay, these brushes are of either it is made up of carbon or copper. Okay, but copper is good brushes because it has less drop across it. Carbon has more drop, so the drop can be 2 volts. Okay, and armature, which is rotating, it is also having some resistance. Okay, so the generated EMF EG, when it is subtracted by the drops which are occurring at the armature resistance and at the brushes, so that resultant amount of EMF or voltage is given to the load. Okay, and in the motor vice versa happens. What happens in the motor, as I have told you in the previous class also, in the motor we give the electricity. Okay, we give the electricity and mechanical work done is there. Okay, so when we are giving this electricity voltage, say V voltage is given by us, then if we subtract the armature drop here as well, then that resultant EMF, here it is denoted by EB, this is known as back EMF. So that back EMF appears across the armature of the motor. Okay, is this clear? Okay, so there are now next topic is our types of DC generator. So we are having 3 types of DC generator. So the MMF is required to establish the flux, and that can be done by various means. So the DC machines or DC generators are classified accordingly. So one is the permanent magnet DC generated, second is the field coils excited by the external sources, and third part is the self-excited generator. Okay, so in the permanent magnet generator, what happens that it is uh, it is having very good magnetic properties, which means that the flux lines, magnetic lines of forces or flux, will travel from north pole to south pole automatically and in abundance. Okay, so flux is moving. So as and when we will provide the means for the rotation of armature, the flux cutting will be there and EMF will be produced. So these machines are compact, low power is generated. This is a disadvantage. Therefore, it is less used and also it is costly. Okay. The example of this permanent magnet generator is the dynamos, which is used in motorcycle, or you can say dynamos in the cycle as well. Okay. So next classification is the separately excited generator. Here the DC machine or DC generator, its field coils are connected to a different DC source. Okay, you can say some DC source in the form of the battery is connected, which will supply the DC field current, DC field current. Okay, so field current will energize these electromagnets, and when it's energized, passage of current will result in the flow of flux, which will result in the energizing of field, and more and more flux will pass through north pole to south pole. Flux cutting will be there and EMF will be generated. Okay, since this process involves the separate source of excitation, so at least it is called separately excited generator, and it is expensive because we are using two setups, one for the external excitation and one for this. Third is the self-excited DC generator. Okay, so the field magnets which are present here, it is in between the separately excited and permanent magnet. You can say that permanent magnet field is the topmost, it is in the number 1, and separately excited is number 3. So this self-excited is in number 2. It also uses the electromagnets, but how it is different from the separately excited DC generator, that in case of these field coils are generated by DC source, this DC source can be external source or it can be three-phase supply is there and it is rectified using the rectifier, as in case of our laboratories. But once the field coil gets the field current, so this magnetic field system is energized, and now these field coils are connected to armature coils. Okay, so once the DC generator is excited, the external source can be disconnected. There is no need further of that setup. Okay, so when the field coil is there, flux is produced due to the rotation of armature, flux cutting is there, EMF is produced, then armature current is produced. Now, since the armature winding is connected to field winding, so a part of the armature coils will be connected to field coils. So when it is connected to field coils, it means that the field current is raised within the setup itself. That is why it does not require any external support now. Okay. So now the field coil is even more than the first stage. So armature current will be produced even bigger. So even bigger amount of field current will be given back to the source. So even more further it will be energized, electromagnetized. Okay, so this process of field current generation and armature current generation will continue till the rated voltage of the generator is reached. Okay, since I have told you that this magnet system is in between the earlier two, so some residual magnetism is present, but it is not very well. Okay, so when the field coils is connected in series, it becomes series generator. When it is connected in parallel, it becomes shunt generator. And if the partly it is connected in series and partly in shunt or parallel, then it is compound wound generator. Okay, so clear? Is it clear to everyone? Okay, so this is the diagram of the series wound generator. Our generator is there, EG is the generated EMF. So the armature coils is connected to series coil. Okay, again what is to be noted here, that current is passing from the generator to the load. Okay, when its current is moving out, it means it is generator. When current is moving in, it means motor. Only the direction of current will decide whether it is DC motor or generator. Okay, now it is shunt wound. Here the shunt field or the field coils are in parallel, and in the short shunt compound wound, the compound wound, I have just told you that it is the combination of series winding and shunt winding. So if the series winding is small and shunt winding is more, it is short shunt compound wound motor as shown. And if the series winding is more, all as shown in this diagram, all of the armature coil is passing through the series coil, and then it is divided into shunt field. It is called long shunt compound wound generator. Okay, so uh, so the windings, when the amount of the current which is to be passed is more, then we apply thick wire system. But if the per coil magnitude of current is less, then we use fine wires of many turns. Okay, series generator and shunt generator applications I have already discussed in the first lecture of the DC machine. Okay, so this is the shaft of the DC machine. It is made up of mild steel, and this portion is known as armature. Okay, and you can see the armature slots. Okay, you can see these armature slots, and in these armature slots, armature winding is there. Okay, is this clear?
Yes.
Okay, now this is our armature, and it is separated, and insulation is provided here. Okay, now you can see insulation is there. Now what is happening in the other part? Other part is, this is our second part. It is, now you can see these slots. Okay, these are slots and the windings is there, but now it is wrapped by the thread. It provides, it is known as overhangs. So it has two purpose. One purpose is that it binds all the winding together, and other part is that it also provides the insulating medium. Okay, so the winding which is passed here, it goes here. Okay, so it is connected here one thread is passing through here. Okay. So now it is connected to this portion, and this portion is known as commutator. Okay. So the poles of the generator, north pole you can say is here, south pole is say below. It is external coverage is just missing. It is just the rotor part, not the stator part. So I am explaining that. So north pole and south pole is there above and below. So flux passage is there. Is this armature is rotating, and when it is rotating, it will cut the flux. And using this commutator, what happens that the rectification is there. So AC current is converted into DC current. Now the brushes is two brushes say, so it is placed above and below. So what it does, this commutator is also made up of the copper segments. Okay, so these pass this rectified current to the external load. Okay, so is this clear to everyone?